Dear physics aspirants, the center of mass is the theory topics of the system of particles and rotational motion. In this segment, you will find we shall first see what the center of mass of a system of particles is. Then they discuss its significance. Here, you will see the photographs. For simplicity, we shall start with the two particle system. We shall take the line joining of two particles to be the x-axis. Here we'll see x1 and x2. And now let us the distances of the two particles of x1 and x2 respectively, m1 and m2, and the masses of two particles. The center of mass of the system is that point C is at a distance x from O. Then capital X you will see, and here O, where x is given by x square. X is equal to m1 x1, m1 x1 and m2 x2, m1 x1 plus m1 m2 x2 by m1 plus m2 divided by. Here you will see this formula will provide you the information. X can be regarded as the mass weight, mean the x1 and x2. If the two particles have the same mass as m1 and m2 is equal to m, then x is equal to mx1 plus mx2 is equal to 2m. And now this time of m is 2m, the x1 plus x2 is by 2. Thus the two particles of the equal mass and center of mass lies exactly midway between them. If we have the particle of the masses m1 and m2, m3, m and f respectively along with a straight line taken as the x-axis, then the definition of the position of the center of the mass of the system of particle is given by the summation line. X is equal to m1 x1 and mn xn, m1 m2 mn, summation like this: m1 total, grand total m1 x1 m1, summation m1 x1 m1 7.2. 7.2 will provide you the information regarding this, where m x1 and x2 are the distances of the particle from the origin. You know, O is the origin, and here you will see the x is also measured from the same origin. X will be measured with the same origin, and the symbol summation, the Greek letter sigma. This is known as the Greek letter sigma, denotes summation, total, grand total, totalization. This is known as the summation and also indicated by this summation m symbol, and sigma the Greek letter. This letter belongs to Greek in this case, and particles the sum of the summation m1 is equal to m as the total mass of the system. Suppose that we have the three particles now lying in a straight line, not lying. We may define x, y, and axis and the plane which the particle lies in. This represents the position of the three particles by coordinates x, y, 1, y, x2, and like this respectively. That is masses of the particle, and m1 and m2 and m3 respectively, the center of the C and the system of the three particles as defined by this, located by the coordinate x, y given by x like this, m. This for the particles equal mass m1, m2, and m3 is m3, and here we'll see this. Okay, and you will solve. After solving, you will find that the three particles of the masses of the center of the coordinates by the co-centroid of the triangle formed by the particle. Here you will see, and not necessarily lying in the plane, but distributed in space. The center of mass of such a system is xy shed, wherein x summation like the sigma. Here m is equal to m sigma m1 is total mass of the system index. R runs the 1 and m as the mass of the particles and positions. Equation 7, 4, and 4, 5, 6 can be combined into one equation using the narration of the Bayesian vectors. The letters R1 to be the Bayesian vectors and I ith particle and R be the position vector of the center of the mass. And now you will see with the formulation, and now sum of the right hand side is vector of the sum, not the economy of expression we achieve by the use of vectors. Vectors formula is here in the original frame reference that coordinate system that shows into the central mass of the summation, and one R1 is 0 and given by this particular rigid body such the meter of 6 array flywheels is a system of closely packed particles. Equation 7 for free C and D are therefore applicable in rigid body. The number of the particles atoms of the molecules in such a body is so large that it is impossible to carry out the summations over the individual particles, and the equation says the spacing of the particle is here, and a small rate of continuous distributions of mass via the subject divide the body into small element mass say m2 2 and 3, and I will say there's a taken but located above the points x y z. Coordinates of the center masses approximate, and the summation is here as we mark the bigger and such as the smaller these expressions become exact, and that case we denote the sums of the verb I by the integral thus dx by dt, and the calculus will be used. Remove the total mass of the baby and the cavernous of the central mass now, and here I will see 7 from A vector expression sequence, and the calculus will be used. We chosen mass region that are 0 in here, and this is often that we have to calculate the center of the mass of homogeneous bodies at the regular space like the rings, disks, and spheres, rods, etc. By the homogeneous body, we mean the body of the country vary by the uniformly distributed mass, and by the using symmetries of configuration we can easily show that the centers of mass of the bodies lies in their geometric center. You will see here x-axis determine the cm of a thin rod. Here I will say let us consider thin rods whose weight and breadth in case the cross sections of a right rectangular radius curve sections of the radius must be smaller than length, taking us to be the geometric center of the road and x-axis to be along length of the can say that the reflection symmetry for every elements of the x-axis and elements of same masses a minus x net contribution of every such pair to the integral, hence the integral x limit itself to 0 from the point which is this integral self is 0 in the center of the mass. Thus the center of the mass homogeneous thin rod coincides with the geometric centers. This can be understood in the basis of reflection symmetry. The same symmetry argument will apply to the homogeneous rings, disc spheres, and even loops. Rectangular curve sections for all cell bodies. You will feel that the variable dm is the point xyz can be always take an element of the same mass of the point minus x minus y minus z. In other words, the origin of a point is the reflection symmetry for these bodies. As a result, integral equation 7.0. This means for all the above bodies, the center of mass coordinate coincides with their geometric center. Okay, so here is a figure given here. Question is here. Next video I will share lots of more. Thank you.